All right, in this work example, we're going to look at some nuclear physics here, namely fission reactions. And so we've got a uranium nucleus there that's bombarded with a neutron, and it's going to fission or split apart into smaller fragments, smaller atoms, molybdenum, lanthanum. We've got two more neutrons, and so this is what can lead to sort of a chain reaction. These neutrons could in turn go and bombard other uranium nuclei, and this is how this kind of physics gets weaponized, or used in nuclear power. But they use control rods to sort of slow the rate of this reaction, so it's controlled in a nuclear power plant. One possible nuclear reaction that takes place in a nuclear reactor is given by that equation. Data for the nuclei and particles are given in this table here, and determine for the nuclear reaction the value of X. So we've got to balance everything in terms of proton number and mass number. And so if we see that there's 92 protons down here, but there's 42 plus 57, remember neutrons are not protons, so their proton number is 0. They are in the nucleus though, so they have mass. 57 plus 42 is 99. So if we have 99 protons, but we only started with 92, well, then we need how many negative ones? So like an electron has a proton number of -1. And so to cancel out, 7 of these positive charges, we would need to have 7 electrons. And so that's the first answer here. It says determine for this nuclear reaction the value of X. It's worthwhile to be mindful of the coefficients in front of the nuclide symbol indicate how many of them there are. Just like in chemistry, when you balance a chemical reaction, the coefficient is like how many molecules of that chemical species do we have? How many contribute to the reaction? How many atoms, how many molecules? So here there are 7, right? This is the X is the coefficient in front of the electrons. Electrons have no mass, well, they kind of do, right? Here is the mass, but it's negligible compared to the mass of the nucleons. So we're doing very precise nuclear calculations. We'll consider the very low mass electron, but when we're just sort of looking at balancing the mass number, it's basically 0. But its proton number is -1. So 7 -1s added to 99 give us the 92 that we see on this side, right? And the 99 comes from 57 plus 42 for these fragments, we say, of the fission reaction. So X equals 7. And remember, that just comes from 99 minus what number equals 92, because we have that many protons on the left side, we need that many protons on the right side, so it has to be 7 -1s to balance it. And then it gets a bit tougher. So the next thing they ask us to do here is to show that the energy equivalent of one unified atomic mass unit is 934 mega electron volts. All right, so we should be able to do that, right? One unified atomic mass unit is 1.66 by 10 to the -27 kilograms. Or is it 1.67? Remember, it shouldn't be too far off. I guess if we don't show that it's 934, we'd say, oh, we missed a little bit there, 1.67. So one unified atomic mass unit is 1.66 by 10 to the -27 kilograms of mass. And then energy, we know, is equal to mc squared. So if we take the mass 1.66 by 10 to the -27 kilos, multiply it by the speed of light squared. So the speed of light, 3 by 10 to the 8 meters per second. So c squared is 9 by 10 to the 16. And then the units there would be meters squared per second squared. A kilogram, meters squared per second squared, is a joule of energy. So that's a derived unit in physics. And the base units there are kilogram, meters squared per second squared. All right. If you all need a calculator to do that multiplication, go ahead and use one. I prefer to just use some mental math here. So let's see, 1.66 by 10 to the -27 times 9 by 10 to the 16 is, carry the 1.494 by 10 to the -10 joules. Yeah, that's right. Check it in the calculator though. Sometimes this late in the day, my mental math fails me. And And then we got to get that into electron volts. And so cancel out joules, go to electron volts. There are 1.6 by 10 to the negative 19 joules in electron volt, right? Because this is the value of elementary charge in coulombs, and we define the electron volt as the energy that an electron gains as it, passes through a potential difference of 1 volt, right? So that's how we do the conversion. So we take our energy in joules and divide it by 1.6 by 10 to the negative 19, and then we get 93375. 4 zeros after it, so 933.75 million, right? So this 10 to the 6 here, you should know is a mega. Okay, so mega is million, mega electron volts. And so what we really have is 933.75, right? 0.75, and then this is mega. And so that indeed is 934 mega electron volts. Question goes on to say, calculate the energy in mega electron volts released in this reaction. Give your answer to 3 significant figures. And so here we'll sort of work back with the information in this table and the balanced equation up there. So we talked about previously how we approach sort of nuclear reactions and using Einstein's famous E equals mc squared equation to solve this. Remember that there's 934 mega electron volts as a unified atomic mass unit. We need to calculate the mass defect. Okay, so there's some mass on the left side of this, and then there's some mass on the right side. And it's very likely, it's certain that the mass over here is going to be less than the mass of this. Okay, and therefore that mass shows up as energy as per Einstein's famous E equals mc squared. So we've got this equation to sort of guide our thinking. And what we have to do is just some addition now. So on the left side, we've got one of these and one of these. And so that's a total of 235.123 plus 1.00863. And that's 236.13163 unified atomic mass units on the left. On the right side over here, we've got 94.945 plus the lanthanum, which is 138.955. And then we've got 2 neutrons, and so we'll add 2 times 1.00863. And we've even got 7 electrons, which have basically negligible mass, but since it's a nuclear calculation with lots of significant digits, we'll be as precise as we possibly can. So then we're going to add into this 7 times 5.49 by 10 raised to the 4. 235.921.103. .210527 unified atomic mass units. That's the change in mass or the mass defect. So you're always trying to calculate a difference in mass, so you can plug it back into Einstein's equation because c squared is just always a constant number. And then that's how you calculate energies for nuclear reactions. So I have this number in my calculator. What we want to do, well, do they want it in electron volts or in joules? So let's check and see where we're sort of going with it. So they want the answer in mega electron volts. Okay. We already know how much energy one unified atomic mass unit is. Like we already did this calculation in part 1. So if we now know that there is 0.210527 unified atomic mass units, and we have this nice little truth now that one unified atomic mass unit is like 934 mega electron volts, then we can just convert directly like that. Take that number in your calculator times 934, and you get 197 mega electron volts of energy released in that reaction. Again, you could do the same thing that we did to sort of realize this, which is convert this into kilograms, plug it in here, multiply it by c squared, get the energy in joules just to convert it back to mega electron volts. But why would you do that? We already kind of did that work. We can do it the simpler way, right? Like this is a nice conversion here. That's always going to be true. You just rely on that. And then lastly, we want to suggest the forms of energy into which the energy calculated in B2 is transformed. And so anytime you're thinking about nuclear reactions, you should think about gamma photons are created. And there's also kinetic energy sort of the byproducts. So when a neutron bombards a uranium nucleus and the nucleus splits apart, those fragments are going to have kinetic energy, and that energy has to come from somewhere because we know that energy is neither created nor destroyed. So we can say the energy shows up as kinetic energy of products. And also some gamma photons, which is not really part of the reaction, but sometimes you'll see it, in the reaction. So gamma looks kind of like this. So gamma photons are the other sort of form of energy into which that energy is converted. Because again, energy is neither created nor destroyed.